Okay, so now let's go ahead and get something displaying on the screen. So when I run this and then do word game, yeah, we just draw the screen. But what I want to do is go ahead and actually set up something on there. So let's go into our Scratch buffer here, and I'm just going to explain a little bit about what we are going to do. So a pixel on an LCD TV or LCD display or TV, or on an old like cathode ray tube TV or monitor, is going to be a series of three lights, which are red, green, and blue. And then those lights are either going to be on or off to various degrees. So if you have a pixel that's completely red, then the red bulb is going to be completely on, and then the blue and the green are going to be completely off, right? And then you can imagine combining colors in this way, right? Where if you have both red and blue completely on, you're going to get like a purplish magenta color. If you have the green off, then yeah, you're going to get that sort of purple. And if you have all of them on equally, then you're going to get white. If all of them are off, then it's a black pixel, right? So what we want to do is bundle data together, which is going to be drawn on the screen, and it is going to be given to the operating system, and then the operating system is going to go and interface with the video device to tell it which bulbs to turn off and on, right? So what we say is that each pixel is going to be four components, which is going to be a red, a green, a blue, and an alpha. And the alpha represents like the opacity of it, right? Which again, that doesn't really make sense in the physical sense. We'll see in a little bit why we care about this alpha. But if you ever see something kind of like faded and translucent, like a ghost or something, or like a level fading out in a video game, alpha is what's being used there. So like you can imagine if you have something red with half alpha, an alpha of like 0.5, so these are on the range 0 to 1, right? So if you had something with, 1 red, 0 green, 0 blue, and an alpha of 0.5, and then something with an alpha of 0.5 and blue behind it, if those objects were at the same space, then they would be like blended together, right? You wouldn't just see the red on top of the blue. You would see a little bit of the blue, shining through the red, right? So, again, right now we are going to care about alpha. We'll get to that in a little bit. Just know that these are the four components that make up a pixel. So each of these is 1 byte. And that's going to be on the range from 0 to 255 whole numbers, right? So if we had a byte that was 255, 255, 255, 255, then that would be white, right? If we had 0, 0, 0, 0, that would be black. If we had 255, 0, 0, 255, that would be red, right? And again, we can pretty much ignore the alpha because that doesn't matter when we're physically drawing it on. We would use the alpha beforehand to sort of combine these colors for things that are in the same spot. And we honestly might not even worry about using alpha for quite a while because I think we can get a lot of mileage out of just these basic colors. So if each pixel is 4 bytes, then that means that we can represent all of our pixels as a array of bytes, right? And then we would just say, hey, if you want to get a pixel, look into the array of pixels at 0, and then you would do the same thing at 1 and 2 and 3, right? And this would give you the red, green, blue, and alpha for the first pixel, right? And then, at 4, we would have the red, then the green, then the blue, right? 5, 6, and then alpha at the 7th again, right? So what we want to do is go ahead and allocate some number of bytes that is going to be enough to fill our screen, right? Well, right now we have this we have a 400 by 400 screen. What I'm going to do is go ahead and pull those out. So we're going to say int screen width and int screen height. And I'll go ahead and say, in fact, we'll do maybe 800 and 600. And then right here we can say screen width, screen height. In fact, what I'll do is actually say this is 800 by 450. So it'll be 16:9, right? Just like, most monitors and TVs are. Okay, so now I want to go ahead and allocate some bytes, right? So these are going to be chars, right? And they're going to be unsigned chars. So we haven't seen this before. But this unsigned is, it's being combined with this type. So this is its own type, an unsigned char, which is saying that, hey, while a char is 1 byte and it's on the range -128 to 127, then this unsigned char is going to be on the range from 0 to 255, right? So we are going to cast the result of our malloc to that, right? We're going to do the malloc, and we are going to say that this is going to be the screen width times the screen height. We can go ahead and pull up a calculator real quick. So if we have a screen that's 100 by 100, right, we need 10,000 pixels. If we have something that is 800 times 450, we're going to need 360,000 pixels, right? And so on. So what I'm actually going to do is go ahead and store this in an int. We'll call this, well, first of all, I'm going to call this bitmap. And we can go into why it's called that in just a second. And I'm going to store this in this thing called bitmap size, which is going to be screen width times screen height, right? And yeah, so bitmap, that's right. We'll pull it up on Wikipedia and get an image of it. That's not a great image of it, actually. While that is an example of a bitmap, maybe we want something a little nicer. Okay, yeah, this is a pretty good example of a bitmap. So here's a bitmap for the letter A, right? And we can just see, here's 1 pixel, 2 pixels, 3 pixels, 4 pixels, 5 pixels, right? And so on. So, and we can see kind of how the letter A goes through all of those pixels. So we want, we want 4 bytes for each pixel. The issue, though, now is that, again, if we pull up the calculator, let's just do 100 times 100 again. So that's 10,000 pixels. But for each single pixel, we want 4 bytes. So we're going to need to multiply that by 4 again, right? So now we have 40,000. And here we're going to need to do the same thing by 4. What I'm going to do, though, just to make this maybe a little more elegant, is we'll have a pixel size, and we'll say 4. And we'll do times pixel size right here, right? Oops, pixel size. And then here I can just say bitmap size. This way we don't have to remember, this multiplication with 3 terms, anytime we want to find out how big this thing is, we can just go ahead and pass in the bitmap size, right? So we should be getting something with 800 by 450 times 4, right? So that's like 1,440,000 bytes. Okay, so let's go ahead and just compile, make sure everything's good. Looks like it is. Cool. All right, so now what we want is to go ahead and let's just say that we are going to iterate over all of those bytes. Sorry, this is, and again, this is why bitmap size is helpful, because I want to iterate over all of the bytes. I can just go ahead and do that, right? And we'll say bitmap of I equals 0. So now everything in our bitmap is set to black. So when we draw it, which we aren't right now, forgot that. When we draw it, we should be seeing a screen that's all black, right? So what we want to do is go ahead back to our, see, where was our list of functions? I think it was right here. Yeah. We want to see, well, let's just search image, right? So we have all of these, and that was the one we wanted. We want create image. And then we also want to look at, I believe it's put image. Yeah. Put image. So right here for create image, it allocates enough memory needed for an X image structure for the specified display. And we tell it how big it is, right? And so if we go ahead and look at this X image, we can see it has a width that has a height. It has some data. You see this is a char star pointer to some image data. And, it's got some other things to it, right? So what we're going to want to do is go ahead and create one of these. And then when we go ahead and put image, we're going to pass in that image, right? So the way this is working is we go ahead, when we create an image, we give it a bitmap, right? We give it this array of chars. If we go back to this function right here, we can see it takes in this data, right? And if we go look at the definition of the structure, it has a pointer to that data. So clearly it's storing the data. It's storing the address of the data that we passed in, right? So what that means is that when we create an X image, and then we go ahead and we put that image on the display, anything that is in bitmap is what the X image is going to look at. It's going to follow that address, and then it's going to start reading bytes from there to see what it should put, right? So let's do this. We'll have an image, and we'll do X create image, right? And okay, so it's going to take a display. Then it's going to take a visual, which we don't have yet, a depth, which we also don't have. Then this thing, this format, let's go ahead and look at it. It specifies the format of the image. You can pass an XY bitmap, XY pixmap, or Z pixmap. Let's see if we can have a definition of that. Z. Okay, so let's see. Z pixmap X11. Okay, yeah. Yeah, so we want to use Z pixmap. Because yeah, if we did XY, we would have all of the red pixels and all of the blue pixels and all of the green, or all of the red components, all of the green. Yeah. I figure that's why I always use ZPixMap. I just wanted to make sure. It's always good to double check when you're doing this stuff again. So the number of pixels to ignore, well, we don't want to ignore any of them, right? The bitmap is our data that we're passing in, right? It's this pointer to the char. Then the width and the height is the width of the image in pixels, right? So that's going to be the same as our screen width and our screen height. And then bitmap pad and bytes per line. So the start of one scan line is separated in client memory from the start of the next scan line by an integer multiple of this many bits, which is a very fancy way of saying, I guess it's not even that fancy, but it's saying that, okay, hey, since we have these 4 components and each of them is a byte, how many bits away is the next pixel? Well, so when we're at the first pixel right here, we know that the next pixel is going to be 32 bits away, right? And then the next thing is just going to be, bytes per line. I think that can just be 0, right? Between the start of one scan line and the start of the next. Yeah, I'm pretty sure that is 0. I think it can be 0. I think we could use that if we wanted to, but if it's 0, we'll just have to do that manually, which is what we want anyway. All right, so now we want to go ahead and make a couple of things that we don't have. So we need a visual and we need a depth, right? So let's go ahead and look at visual. Well, I think I just saw it right there. Okay, yeah, default visual. So this returns the visual type for the specified screen. In this case, we're going to give it our screen, right? And we want to get the visual from it. If we go ahead and look at the visual structure right here, you can go ahead and read the description. And, this just contains possible color mapping. We don't really care about that, but you see, we can have like grayscale and pseudo color, direct color, etc. We're just going to use the default that it's going to give us. Should be totally fine for our purposes. So I'm going to go ahead and put this stuff up right after we map our window. It's going to be default visual, display, and screen. Then the other thing we want is the depth, which is going to be the default depth of display and screen, right? And we can go ahead and just look at that. Yeah. So this is the number of planes of the default root window. By plane, we can think of the image as having like layers to it, like layers of a cake or pieces of paper stacked on top of each other. All we're ever going to really want to do is just have one layer. Maybe in our game we have multiple layers, but that has nothing to do with the operating system's idea of what we're drawing to the screen, right? So that gives us our visual. That gives us our depth. We have everything else, so we should have created the image. So let's go ahead and compile. Let's see. Invalid initializer. What did I do wrong there? Where are we? Create image. All right, so we have display visual depth format. Display visual depth format. Offset data width height. Offset data width height. and bitmap pad, which is an int. What did I... Let's go ahead and x create image invalid initializer. I've never seen that error before. Well, that has nothing to do with xlib. I feel like this is just a very simple and stupid typo. Well, let's see what happens if we get rid of those. It should complain. Too few arguments passed in. So, okay, what if we just do 32 right there? Okay, what if we just do that, right? Maybe this shouldn't be unsigned. Maybe that's what's... No, that shouldn't matter. I'm making sure we do want that to be unsigned. Oh, duh, I bet I know what it is. This thing is probably returning us a pointer to an image. Yes, it is. So we want the pointer to the image. That's a pretty bad error message that it's giving us. Really, just the weird thing is that it's saying that the problem is here on column 20. Oh, well, I guess that's... Oh, that's just a line wrapping issue. Oh, that's really gross. Because column 20, you can see it says line 323, column 20. Just because my terminal is wrapping around. So this is column 20 right here. So it's, you know, that makes sense. Even though it's unfortunate, it does make sense. So now if we go ahead and look at our X put image, it's going to take the display, the drawable, which we haven't seen yet, the GC, the graphical context, X image. Then it's going to take the source, so where we want to put the image on the window. The source is going to be the point on the image we want to start reading from. Then it's going to take the destination X and Y, which is where we want to start putting it, and then the width and the height of the image. And since we just want to put up one image on the screen that we're going to write everything into, just because it's going to be faster that way, we're just going to do 0 for all of these, and then the screen width and the screen height, which are the same dimensions of the image, right? So if we go ahead right here, so we want to do this after we get the input, right? We want to say X put image display something that's a drawable, which we haven't seen yet. The context, did I call it context? Yeah, I did. Then 0, 0, 0, 0, screen height, screen width, right? And now let's see what a drawable is. Xlib drawable. I know what it is. I just want to go ahead and find the documentation for it. Drawable. Oh, here's the glossary I've been looking for. Both windows and pixmaps can be used as sources and destinations in graphics operations. So this is kind of like an ambiguous type that can be one or the other, right? So in this case, we just want to go ahead and do our window, right? See, what did I get wrong? Too few arguments. Let's go ahead, look back at it. Oh, did I forget to pass in the bitmap? I sure did. I mean, sorry, not the bitmap, the image. So Okay. We are getting something, though maybe not exactly what we expected. So let's go ahead and, first of all, maybe what I'll do is just set that to not be unsigned anymore. Okay, that doesn't matter. Again, like I said, it's been a little while since I've done this. I just want to make sure I wasn't totally off base on that. Bitmap size, again, I'm going to do, just for my own sanity, unsigned char. Let's think about this. Am I passing in everything in the right order? I'm doing width and then height. I'm doing height and width there, which is silly. There we go. All black screen. Cool. Very neat. All right. So now we could go ahead and do something. Like, let's just say that if I modulo 2 is 0, which is going to be saying, hey, if the remainder of I divided by 2 is 0, then we want to set it to 255, else we're going to set it to 0, right? So if the remainder of if I divide by 2, if the remainder is 0, then it's even, right? So we're going to be doing this for every other component. Okay, yeah, so I think that makes sense. Let's just go ahead and think about it. So when we get the first component, which is going to be red, so it's going to be 0, 1, 2, 3. It's the first 4 components of the pixel. We have 4, 5, 6, 7. We're going to have 8, 9, 10, 11, right, etc. So yeah, we're always going to set the red to be 255, and we are always going to set the blue to be 255. So we get that really awful looking color. What if we do something like 4? Okay, yeah, so we get blue, and, you know, we can do stuff like that. So you can go ahead and play around with this if you want to. Let's go ahead and say, I don't know, the color is I, right? So remember that we are going to be wrapping around, right, when we're using I to set the pixel, right? So if we have an I that is 250, or yeah, if we have an I that's 256, then that's going to become 0, right? Because we're going to wrap around because we've ran out of bits, right? We're going to have, because 255 is going to be, what, 1, 1, 1, 1, 1, 1, 1, 1, right? And so if we try to add 1 to it, we're just going to get that, right? And so we aren't going to be, like, oversaturating, right? That doesn't really make sense in this context, but just don't be worried, like, none of these values are ever going to be greater than 255 because we're just going to keep overflowing the number as I gets bigger, right? Okay, and we get this cool looking gray, right? Or like scan line sorts of things. And we can sort of figure out why that is because the first pixel is all going to be 0. Then the next pixel is going to be 1. It's all 1. And then all 2, all 3, all 4, right? All the way until we get up to here, right? And then we are going to be overflowing and we're back to black, right? So like right here, everything's 255. Then we overflow and move on to the next one, right? So that should be good for right now. And in the next video, we can go ahead and start drawing start writing code that lets us draw things in maybe a more structured sort of way.